In this lecture, you'll learn about the private address ranges. These were documented by the IETF, that's the Internet Engineering Task Force, in RFC 1918. RFC stands for Request for Comments. So when the IETF release some documentation, they release it as an RFC number, meaning that other engineers can comment on it and maybe suggest improvements. But the RFC is still a finished standard as well. So the final standard, as of today, for private IP addressing is RFC 1918. There are a load of other RFCs out there as well for pretty much every technology, but if you asked me to name an RFC number, then the only one that I probably could is RFC 1918 for private addresses. Because if you're in conversation with somebody, it's quite common to call it an RFC 1918 address. Sticking with our theme of how the internet was originally designed to work. Private IP addresses were originally for hosts that should not be connected to the internet. Because obviously if you're an organization and you've got a part of your network that you don't want to be connected to the internet, you're not going to pay for public IP addresses for those hosts. That would be a waste of money paying for IP addresses that are never going to be used. So a way that you could save money is by using private IP addresses on there instead. The other benefit you get from it is that the hosts are not going to be connected to the internet, so it makes them more secure as well, and it locks down that they can't talk on the internet. So if you're thinking, well, why would anybody ever do that? Maybe it's a highly secure environment, like maybe it's a bank, and the bank has got a part of their network that they want to keep completely off the internet for security reasons. They would use private IP addresses there. Another possible example is maybe you've got a high school and they've got PCs there, but the school authorities don't want the kids to be able to get on the internet. Again, they would use private IP addresses there. So the addresses that are private, there's a range in each of the different classes A, B, and C. In class A, we've got 10.0.0.0 to 10.255.255.255. And that uses the standard class A subnet mask of /8. So we can also write it as 10.0.0.0/8 or 10.0.0.0 with the subnet mask 255.0.0.0. The class B private range is 172.16.0.0 to 172.31.255.255. That is 172.16.0.0/12. So the class B range does not use the default subnet mask of /16. And the class C range of private addresses is 192.168.0.0 to 192.168.255.255. So the class C range again, it's not the default mask, it uses a /16, which is the normal default mask for a class B network. Okay, so those are the three ranges of private addresses. You want to have these committed to memory. So just like you're going to commit to memory what the range is for class A, class B, and class C, also remember what the ranges are that are used for the private addresses. This is not just for the CCNA exam. You're expected to know this off the top of your head when you're working in the real world as well, because you'll see that RFC 19 addresses are used a lot in the real world. I'll get to the reason for that very soon in this lecture. So let's look at an example of where we would use private addresses back in the day when we wanted to keep our hosts off of the internet. So this is a secure environment. We've got Bank A on the left, we've got Bank B on the right. Bank A have got a public part of their network that is used for their staff who are allowed to access the internet. That's at 175.11.0.0/24. And then they've got a different part of their network, which is maybe where they have some very sensitive servers that they want to keep off the internet, and they put on there the private address 10.10.10.0. Bank B, their public address is 196.14.10.0, and they've also got a private range, which is 172.18.5.0/24. Okay, an example number 2, you can see that here Bank A and Bank B are both using 192.168.10.0. That's fine. They don't have any connectivity to each other anyway because we're on completely separate networks. So you'll find that with private addresses, loads of organizations all over the world will be using the same private address ranges. They can't use the same public address ranges because they need to have connectivity to each other over the internet. But the private addresses don't have any connectivity outside that organization, so those addresses can be reused over and over again. Okay, let's revisit the IPv4 global address space problem. So the designers of IPv4 did not realize how big the internet was going to get. And when they first designed the IPv4 format, they thought that 4.3 billion addresses is going to be more than enough for what would be required. But the problem is, we know today that 4.3 billion is nowhere near enough. So another problem is that the protocol is not efficient in the way that it allocates addresses as well. Again, because they thought that they had more than enough addresses, they didn't worry about wasting addresses. For example, the 127 address, wasting an entire class A range just for loopback testing. Also, the way that large address blocks were given out to organizations who were not using anywhere near as many as the actual addresses they were given. So the IPv4 address space, it's not big enough for how many addresses we actually need on the internet today. So they ran out of addresses. So quite a while ago, in fact, back in the late 80s, they realized that they were going to run out of addresses. So they started working on a solution to the problem. And in the 1990s, the solution that was developed was IPv6. So the addresses we've been talking about up to this point in the course has been IPv4. IPv6 addresses have got a different format. Where IPv4 addresses are 32 bits long, IPv6 are 128 bits long. But the address space is not just 4 times as big as the IPv4 is, it's actually exponentially bigger than that because we keep doubling it every time we add a bit. And the IPv6 address space is actually 7.9 times 10 to the power of 28 times as many addresses as IPv4. So there's a huge amount of addresses with IPv6, and it was developed in such a way that they should never run out of addresses again. But there's also a problem with IPv6, just like there was a problem with IPv4. And the main issue is that there's not a seamless migration path from IPv4 to IPv6. So if you're an organization, you've already got your host deployed and you've got IPv4 addresses on there and you've done all of your IPv4 addressing design, it's not easy. You can't just flick a switch and convert that to IPv6 because the address format is completely different. It's not seamlessly backwards compatible with IPv4. So it's quite a big project to migrate from IPv4 to IPv6 if you're already an existing organization. So because of that, NAT, Network Address Translation, was implemented as a temporary stopgap before everybody could convert to IPv6. And the way it works is an organization can use those RFC 1918 private IP addresses on their inside network, which are not publicly routable, so they don't work on the public internet. But what they can do with those addresses is on the way out, they can convert them to the public IP address on the outside. So if you're using a private IP address on the inside, whenever you communicate with anybody out on the public internet, when the traffic gets to them, it looks like it's coming from a public IP address, so they're able to send the traffic back to you. And many hosts on the inside, so many hosts on the inside using those private IP addresses can share a few or even just a single public IP address on the outside. So let's have a look and see how this works. So you see we've got Office A on the left, and they've bought a small range of public IP addresses, which is 175.11.0.1/28, which gives them 14 addresses. and they're using the private addresses on the inside of 192.168.10.0/24, and they've got 200 hosts on the inside. Well, they're able to convert or translate those private addresses on the inside to the public addresses on the outside whenever they communicate with anybody on the internet. So if we didn't have private addresses in NAT, they would have required 200 public IP addresses for those hosts on the inside. But now they're doing it with just 14, and actually they could have done it with just one if they wanted to. So by using private addresses in NAT, this saves loads of addresses in the IPv4 public address space. It also saves organizations money as well because they don't need to pay for those public IP addresses. Let's talk about how things are actually done most commonly today then. Back in the early 2000s, a lot of industry experts predicted that everybody would be using IPv6 within a few years because of the shortage of IPv4 addresses. But it hasn't actually worked out that way. And in today's networks, most enterprises are actually using RFC 1918 IPv4 addresses with NAT. So if you go and you work for a company, the chances are you're going to see something very similar to the previous slide, where you're using private IP addresses on all of your inside hosts, and you're translating them to the public IP address on the outside when they go out to the internet. Reasons for this are RFC 1918 actually has a security benefit of hiding your inside hosts by default, because those private IP addresses are not routable on the internet. If you send traffic to a private IP address and it gets out to the internet router is just going to drop that traffic. Okay, so your private IP addresses, you can route between your hosts on the inside network, and you can route between your hosts over your own wide area network, but you cannot send traffic to a private IP address on the internet. Because all the different companies are using those private IP addresses, the internet would not know which one to send it to. So they're for internal use within the organization only. Another reason that there's been a slower than expected uptake of IPv6 is that IPv6 address format is completely different. We've actually got a section that focuses on IPv6 later, and you're going to see that, but it's completely alien to the IPv4 format. And all of the network engineers that are around today are very, very comfortable with IPv4. They're used to working with it day in and day out, but a lot of them are not comfortable with working with IPv6 because their organization isn't using it yet. So if you go and speak to one of these engineers and say, hey, we need to convert to IPv6, they're probably not going to be too keen on the idea because it's something completely new for them. They're already comfortable with IPv4, and they can give you the answer, well, we're already using private addresses in NAT, it's not causing any issues, everything's working just fine, so why put all the time, effort, and money into converting IPv6? So that's why it's been slower for everybody on the internet to move over to IPv6 than was originally expected. But IPv6 is still found in a lot of places, mostly in service provider networks. The majority of service provider networks will support both IPv4 and IPv6. You'll also see it being used for mobile services, like on your mobile phone, because there's lots of mobile phones and they're a relatively newer technology. So IPv6 was already out, there was already the shortage of IPv4 addresses, so for mobile services, they're mostly on IPv6. Where you'll also see it is in larger countries, which had a later adoption of the internet, such as India and China. Okay, last thing, spare public IPv4 addresses were exhausted in 2011, so IPv6 is still the future path. So you see that most companies today are using the RFC 1918 addresses and NAT, but it will slowly move over to IPv6. Other points, you still need to understand subnetting. So don't think, oh well, if we don't have that IPv4 address space problem, why did I have to spend all that time in this section learning about subnetting? You're still going to do subnetting even when you're using private IP addresses on the inside, because you still need to do your logical addressing. And you also need to be able to understand and to troubleshoot IP. So everything that you have learned in this section is very applicable to the real world, and also, of course, for passing your CCNA exam. Because we have the entire private IP address space to work with, it's common to see today's real-world enterprises using /24 subnets for their end hosts, a /30 for a point-to-point link, and a /32 for the loopbacks. Remember, we'll talk about loopbacks more later. They're not complicated anyway. It's just a management address on the router or the switch. Complex VSLM. So remember we did that VSLM lesson earlier where I gave you the scenario and I said work out what the subnet mask sizes will be for the different departments in New York and Boston, and say where the network addresses are going to begin at. That would be complex VLSM, where we've got one subnet and we're dividing it up into smaller subnets with different size subnet masks. And it's quite complicated when you do that because you have to think, okay, well, where does the actual network portion of the address begin and end? What's the broadcast address, etc. If you're using a /24, it's super obvious. You just look at it and you know that up to the end of the third octet is the network address and the fourth octet is the host address. So it's very simple to use a /24. When we're using private addresses on the inside, we don't have the problem of a lack of IP addresses. We can use the entire private address space. So it's very common to use a /24 just because it's the easiest thing to do. And easy is good because it makes less mistakes and it makes troubleshooting easier. Where you will see VLSM being used is if an organization is actually using public IP addresses on the inside, which does sometimes still happen, and they need to maximize the use of their public IP addresses because they don't want to waste any because they're paying for them, then you might see more complex VLSM being used in that kind of scenario. Okay, this is the last thing to tell you here about using contiguous addresses. So when you are using private addresses on the inside, like you see here, you're still going to want to do route summarization for the same reasons that we spoke about when we did the CIDR lecture earlier, which is that you're going to compartmentalize the different parts of your network. From one part of your network to a different part of your network, you're only going to send a summary address rather than every single route. So the example here, we've got region A on the left, and it's using 10.0.0/24, 10.0.1/24, etc., up to 10.0.255.0/24. Region B within the same organization on the right is using 10.1.0, 10.1.1, and so on. We connect the two routers between region A and region B. And from region A, we can advertise 10.0.0.0/16. And from region B to region A, we advertise 10.1.0.0/16. So rather than advertising all 255 or 56 routes in both directions, we only advertise one route. So it takes up less memory on the routers because we've got less routes that are known to the routers. And also if there's a problem, the impact stays local to that particular region. So to be able to do this, you need to be careful with the way that you plan your network addressing, and you need to make sure that you allocate them in contiguous blocks like you see here. A mistake would be doing it like you see here. So here on the left, I've got 10.0.0, 10.1.0, then 10.0.2, and then 10.1.3. And on the right, I've got 10.1.0, 10.0.1, etc. So I'm mixing up my 10.0s and my 10.1s. So because of this, I can't advertise 10.0 from left to right because some of the 10.0s are already in the right. If you made a mistake with your network address planning, like has been done here, you would need to advertise all of the routes everywhere. That's going to end up taking a lot more resources in your routers, and it's going to make the network a lot less stable and harder to troubleshoot. So be careful when you're doing your network addressing design, and carefully plan it out at the start and make sure that your addressing is done in contiguous blocks so that you can do your summarization. Okay, that's it. That is us done on the IP addressing and the subnetting. I just have one more lecture to tell you where you can find additional resources. Thanks for watching. If you want to get hands-on practice with Cisco networks for free, then you can download my 400-page CCNA Lab Guide, which you can see above my head right now. Also, check out the video about my CCNA course. It's the highest rated course online. Thanks.